Hello, this is Precalculus, section 6.6. Our focus is on Moivre's theorem, and hopefully by the time we're done with this lesson, you'll be able to represent complex numbers in a complex plane and write them in trigonometric form. You'll be able to use trigonometric form to simplify some algebraic operations with complex numbers. We're not going to focus on finding nth roots, but other than that, we'll cover pretty much every topic in this section. So to start off, I just want to remind you about the complex plane. Basically, the complex plane you can think of as your x and y coordinate axis, only instead of using x and y along the x-axis, we call that the real axis, and along the y-axis, we call that the imaginary axis. So you know that when you have a complex number, it comes in the form a plus bi. And so in order to plot this point in the complex plane, the a number is your horizontal movement, and the b number, or the bi number, is your vertical movement. And just like traditionally, if a is positive, you move to the right. If a is negative, you move to the left that amount. If the bi part, if the b is positive, you move up that amount. If it's negative, you move down that amount, as shown here in this example of plotting the point, or plotting the complex number 2 plus 3i. You move to the right 2, and you move up 3. We also can take the absolute value or modulus of a complex number. I like to use the term modulus because absolute value, you think of something different generally when you think absolute value, although it is the same concept. Where the absolute value of a complex number is how far away that number is from the origin, where the absolute value of a normal number that you're used to is how far away that number is from 0. It's the same concept. I just don't want you to think you can just make the complex number negative like you could with the numbers you've been used to working with. So with that in mind, you've done this before. You've found how far away a point is from the origin, and that's what the absolute value or modulus of a complex number is. It's finding how far away it is from the origin. To do that, you take the a and the b in the form a plus bi, and basically use your Pythagorean theorem. Remember, if we're plotting a point a plus bi, if we look up here, we plot this point. Remember, we're going to the right 2 and up 3. Well, the modulus is how far from the origin that number is. So you can easily see you'd have a right triangle. You would take 2 squared plus 3 squared to the square root of that will give you the length of that side. That's what the absolute value or modulus is of a complex number. That's also shown here. Keep in mind when you graph, and remember, we use z, the letter z, oftentimes to just represent a complex number. So something that you can relate to again, that horizontal movement you've used in polar graphing. You know that horizontal movement can be represented by r cosine theta and the vertical movement r sine theta. Well, since we're going a distance away from the origin or the pole, like in polar graphing, we can find or represent a complex number using those terms as well. So a could be represented by r cosine theta, and b can be represented by r sine theta, where r is that modulus or that distance from the origin to the point z, and theta is the angle formed from the horizontal. So with what I just mentioned in mind, we get the trigonometric form of a complex number. So the trigonometric form of a complex number, make sure you write these things down, is, so let's back up. You know how we can write the complex number z as a plus bi. Well, that a plus bi can also be written in this form. That's trigonometric form, where you take r times the quantity cosine theta plus I sine theta, where if you were to multiply r times cosine theta, you would get a, and if you were to multiply r times I sine theta, you would get b. I guess I have those written down right here. So with that in mind, along with how you get r, the square root of a squared plus b squared, and how you get theta, where tangent theta, maybe I'll erase some of this so you write those key things down. Where tangent theta equals b over a. So if you know b and a, or a and b, then you take the tangent inverse of b over a to get theta. And if you know a and b, you're going to take the square root of a squared plus b squared to get r. Once you have r and theta, you can write the complex number in trigonometric form. Some other things to note. We call r the absolute value or the modulus, which we mentioned of z, and we call theta the argument of z. Call theta the argument of z. Of course, as always, if you need to pause the video, feel free to do so to write down these notes. Here's an example of finding trigonometric form. We need to find the trigonometric form with theta between 0 and 2 pi for the complex number 1 plus root 3 I. Well, we know that a equals 1 and b equals the square root of 3. So the first thing that we would want to do is find r. Well, remember, r is going to equal the absolute value or the modulus of our complex number, 1 plus root 3i. How do we get that? By taking the square root of a squared plus b squared. So our r value is 2 in this case. How do we find theta? Well, we're going to do what we just got done talking about. Let's take the tangent inverse of root 3 over 1. Well, we don't actually have to do that. We know that if tangent theta equals root 3 over 1, then theta must be pi over 3, because it's a unit circle value. So therefore, the complex number 1 plus root 3i is also 2 times cosine pi over 3 plus I sine pi over 3. Remember, when we write our trigonometric form, we factor out that r, or we leave it out, I guess you could say. So to write it in this form, once we found r and theta, we just plug those in. Here's r, and here's theta. Everything else is always the same. A couple more things to note and write down. If we can take the product or quotient of complex numbers as well. If we have our complex numbers in trigonometric form, we'll say z1 is here, z2 is here, then we can quite easily take the product. That's what number 1 here shows. We can take the product of two complex numbers by multiplying the r's out front, and then adding the two angles together and replacing the angles with their sum. It's a very easy way to find the product of complex numbers. The quotient of complex numbers, also not difficult. Number 2 here describes that. If we take z1 over z2, well then we take r1 over r2, that number out front, and we find the difference in the angles and replace the angle with that. So we'll go through an example of that next. Here's an example that I have already written out just to save you a little time, or save all of us a little time. If I want to take the product of z1 and z2, well, here's z1, here's z2. Remember, if I'm taking the product, this is the formula that I'm going to use. So this isn't something new. This is the formula that I'm going to plug in. I'm going to plug in r1, where this would be r1. And I'm going to plug in r2, where this would be r2. I'm going to plug in theta sub 1, and I'm going to plug in theta sub 2. I plug those in to each of the spots in the formula, simplify, and I'm done. 4 times root 2 gives me 4 root 2. Pi over 4 plus pi over 6 gives me 5 pi over 12. There's not much farther to go. You can multiply those out or get what those actual answers are as decimals, as I've done here. But other than that, you can't go much farther. So what I expect of you is, I want to see this step right here where you simplified the angles and the r value, and I also would like to see this step right here. What is that approximate complex number, also in the form a plus bi? And the last thing you're going to need to know for section 6 is de Moivre's theorem. Basically, what de Moivre's theorem is used for is to take a complex number to a power. What you can do, it's quite simple. If you're going to take a complex number to a power, here's the deal. This is the complex number right here. If I'm raising that to the nth power, as shown here, all you need to do is raise the number out front to the nth power, that r value, and then multiply the thetas on the inside by n. That's it. Do that, simplify, and you're done. Here's an example. If I want to take this complex number, negative root 3 over 2 minus I times 1/2 to the 4th power, well, I would first need to figure out what is theta and what is r. So I would do that. Theta would be 7 pi over 6. Remember how you can get that is you take the tangent inverse of b over a. And then keep in mind when you're working with that, both a and b were negative, so that tells me I should be in the 3rd quadrant. Don't forget about that stuff you learned about the unit circle. Then how do I get its modulus, or that r value? Square root of a squared plus b squared. That gave us 1. So once I know the modulus, or that r value, and I know theta, I simply need to plug them in. I'm going to take that theta times 4, since we're going to the 4th power, in both of these spots. And if the modulus was any number other than 1, remember back to the formula here, I would be taking that value to the nth power. So technically what I have out front here, I'd have a bracket and a 1 to the 4th power, which just equals 1, so I didn't really need it. That simplifies down as follows. So this shows how taking negative root 3 over 2 minus I times 1/2 to the 4th power equals negative 1/2 plus I times root 3 over 2. And that's pretty much what you need for section 6. This video will be available on the class webpage. Good luck.